This is Matheos.com, where you can find more links to math and computer science YouTube videos. Let's take a look at vector valued functions. There we go. And had to start this video over because I didn't have my workspace situated. I see why now my paper's upside down. My little tablet has a paper on it. So vector valued function. This is where, instead of just like a single vector in 3D, and you can have this in 2D also, we're going to have functions associated with each of our different pieces. We've got f of t I plus g of t j plus h of t k. Now the r, I, j, and k are vectors. And the f of t, g of t, and h of t are called our component functions. So those are our component functions. And let me show you an example of one of these, so I know what in the world we're dealing with before we start working problems. This is a WinPlot. If I go into Window 3 Dimensions, and I do Equation, and there's one that says Curve down here. Let's see, I have cosine of t, sine of t, and t, and yeah, 0 to 2 pi, that's probably good to start with. Let's say OK. Now if I do View, and axis, and then axis, I'm not sure why it gets rid of it, but you can see that. Now if I look at it from this dimension, in terms of my x's and y's, well, we have cosine, sine, and t. What this would look like as our example over here would be dealing with, what did I say, cosine. So we'd have cosine t I plus sine tj plus tk. That's what that graph is. Now when I look at just these two axes right here, this is our x and this is our y and this is our z. So I'm ignoring this last piece. And if I look at this first piece here, we got cosine t and we got sine t. Let me write this down here. We got x is equal to cosine t and y is equal to sine t. And we could square both sides. So this becomes x squared is equal to cosine squared, and y squared is equal to sine squared. Well, then if I add these two together, so I'm going to have x squared equals cosine squared t, and I'll put this equation right below it, y squared and sine squared. Now you can add together the corresponding sides. So this would be x squared plus y squared equals cosine squared t plus sine squared t. Well, cosine squared plus sine squared is equal to 1. Well, this is a circle of radius 1. And if I look over here, it does look like a circle. Now, of course, I can't see the tick marks, but this would be radius 1. That's if I'm looking at just the x and y component. This is kind of slow. I'm going the right direction. And we'll go the other direction. There we go. Now, if I start taking into the account the z component, that's this t here. That's what just makes it kind of curl around. But again, it has a circular pattern if I look at it from up above. Now, if I looked at it in terms of just the y and the z, then it would be corresponding to this right here. Let me see if I can get that. Okay, there we go. X is coming out toward us now. So here's y, and then this axis going up and down is our z. What does that look like? It looks like, let's see, we're ignoring this one. See, it's a sine curve, isn't it? If I were to ignore the y component here and look at the x and the z, then I would see a similar type of deal. Now, to graph these by hand isn't that easy. We're going to use technology to do it here in this class, and this is good as any for coming up with our graph. It's not perfect. There's one graph I looked at, it didn't come out the way I thought it should. But anyway, that's an example. Okay. Now, these first problems talk about finding the domain of a vector valued function. And key is first find the domain of each component function. That's whatever's in front of our I, whatever's in front of our j, and whatever in front of our k. And then the domain of the vector valued function is the intersection of all the domains from step 1. Well, let's review a little bit how to find a domain, because you need to know that for these problems. We've got f of x is equal to 2 over x minus 7. Now, if we have a fraction, what you do is you set your denominator equal to 0 and solve it. So we'll set x minus 7 equal to 0, and that gives us x equals 7. Now, this right here, domain-wise, then would, this is the value we found, is what causes a 0 in the denominator. So our domain would be everything except for this value. You know, we could write it this way: x cannot equal to 7, or in interval notation, negative infinity to 7, parentheses on these, and 7 to positive infinity, like that. Now, this next one, g of x. G of x is equal to square root of 4x minus 3. When you have a radical with an even index, then you can't have what's inside be negative. It can be 0, it can be positive. So what we do is we set the whatever's inside the radical greater than or equal to 0, and then we solve it. So we got 4x is greater than or equal to 3, or x is greater than or equal to 3/4. Interval notation wise, that would look like this: bracket on the 3/4, and then it goes to positive infinity. H of x is equal to square root of x squared minus 3x. This is same idea as that. We're going to take what's inside the radical and set it greater than or equal to 0. Now, since this is a polynomial where we have a power greater than 1, you could have 2, 3, or whatever. What we do is we factor this. So factor an x out. And we'll set each one of these equal to 0. So we'll set the x equal to 0. We'll set the x minus 3 equal to 0. So we got 0, and we got 3. So here would be 0, and here would be 3. Our graph would look like this. Now, when we got a greater than or equal to 0 here, we're looking where our graph is above the x-axis. This is the x-axis right here, this horizontal line. Well, this is above here, and it's above here. So our domain would go from negative infinity to 0. It's a greater than or equal to, so it includes 0, so it'll be bracket on the 0, union, and then 3 to positive infinity. I of x is equal to natural log of x minus 5. Now, we can't have log of 0 or log of negative number. So whenever you have a log, no matter what the base, you're going to take what follows a log, and this be greater than 0. So where you get x is greater than 5, so we'd have parentheses 5 to positive infinity. And our last review, I picked a trig function. Sine and cosine are boring because the domain is negative infinity, positive infinity. But tangent's a little bit different. Tangent is equal to sine over cosine. So this is invalid where cosine is equal to 0. And we're looking between 0 and 2 pi. Cosine is equal to 0 at pi over 2 and 3 pi over 2. So it's, when we're talking about the domain, it wouldn't include these values. Now there's the book has an interesting way of writing these. What they do is they have pi in over 2, and then they have pi in plus, and for example, this is going to go from pi over 2 to 3 pi over 2. So if I have a 1 here, for example, then this would be like n plus 2 over 2. So that's one way of writing everything from pi over 2 to 3 pi over 2. Now, we got pi over 2 to 3 pi over 2. But if I put a 2 in here, then it doesn't work. But if I put a 3 in here, this would be 3 pi over 2, and this would be the 5 pi over 2. So what we're indicating here is n is odd. So that's the way they'll write that. Now, I'd have to do some more thinking about this, see if to make sure this covers all our cases. But for purposes of this example, we don't need to worry about that. This is going to go from negative infinity. Try it again. We start at 0. Does it include 0? Yeah, include 0. Okay, so it should be a bracket there, and then it's going to go to pi over 2, parentheses, because it doesn't include pi over 2, union, parentheses, pi over 2 to 3 pi over 2, union, 3 pi over 2 to 2 pi. And 2 pi will have a parentheses on it because it doesn't include 2 pi. Let me save this. Excuse me. Vector valued functions. And not problems, but page 01. There we go. Okay, so now we reviewed how to find a domain. Let's take a look at an example. So we've got r of t is equal to 1 over t squared minus 4i plus t over 3 j plus tk. Now our different component functions, this is our first one. We'll label that as f of t. This is our second one, that'd be g of t. And our third one would be h of t. So if I look at f of t, That's 1 over t squared minus 4. Well, remember with a domain, we set the denominator equal to 0. If I set t squared minus 4 equal to 0 and solved it, I'd end up with t is equal to plus or minus 2. So if I put 2 in here or negative 2, that's going to give me a 0 in the denominator. So my domain here is going to go from negative infinity to negative 2, union, negative 2 to 2, union, 2 to positive infinity. G of t is t over 3. And I should show the steps over there. I could be lazy. Set the denominator equal to 0. This is square root property. Take the negative 4 over, it becomes a positive 4. Drop our squared, put a plus or minus square root on the other side. So we get t is equal to plus or minus 2. So this is how you write such that it excludes negative 2 and 2. Now the domain for t over 3. For a fraction, you set denominator equal to 0, but we don't have a variable in denominator. So domain here is just negative infinity to positive infinity. And our h of t is equal to t, which is negative infinity to positive infinity. Now our domain is the intersection of all three of these. Well, the intersection is this right here. So negative infinity, negative 2, union, negative 2 to 2, union, 2 to positive infinity. Let's take a look at this one. Got r of t is equal to f of t and g of t. This is not multiplication. This is a cross product. And f of t is equal to natural log of t minus 2i plus tj minus 6tk. And I'm not saying it, but the I, j, k, and so forth are vectors. And g of t. That's square root of t plus 7 I minus tk. There we go. Now remember, to find a cross product, it's a determinant. And the first row is always I, j, and k. Now our first vector here, f of t, we're going to put that here. So we're going to have natural log of t minus 2. We'll have t and negative 6t. So we put our component functions down. G of t. Our first one is the I, so we'll have square root of t plus 7. J we're missing, so we'll put a 0 there. And then the for the k, I'm going to have negative t. Well, if you remember when you're finding the determinant of this, like we're working with the I, we cross out the row and column it's in. And what isn't crossed out, we find the determinant of that. So this would be I'm trying to think if I have room to show it. I think I will. Okay, so again, working with I, so we cross out that row and that column, and so we're left with t, negative 6t, 0, and negative t. Minus j. The signs change. This first one would be positive. This is negative, and then positive. It always alternates, and the first one's always positive. Now if I cross out the row and column that the j is in, then we're going to be left with the determinant of natural log of t minus 2, negative 6t, square root of t plus 7, and negative t. And then plus k, and again if we cross out the row and column that the k is in, we're going to have natural log of t minus 2, t, square root of t plus 7 and 0. So, if I multiply those, I get negative t squared I. If I multiply these together, that gives me negative t natural log of t minus 2 minus, and this when I multiply this together, it's already a negative, so negative negative becomes a positive, 6t square root of t plus 7, and that's j. And then over here, natural log of t minus 2 times 0 is 0 minus t times square root of t plus 7. So this becomes a minus t times the square root of t plus 7 k. So a little bit more complex vector valued function here. Our f of t is equal to negative t squared. And our domain for that would be negative infinity to positive infinity. Our g of t is going to equal to negative t natural log of t minus 2 plus 6t square root of t plus 7. Now the natural log, we're going to take that, it's the t minus 2, and trying to think if I have room, I'll put it over here. T minus 2, and we can't have natural log of 0 or a negative number, so this has got to be greater than 0. So we got t is greater than 2. And for this one, square root of t plus 7, well, we want to set that greater than or equal to 0. So we'll set t plus 7 greater than or equal to 0, and we get t is greater than or equal to negative 7. Well, which one to use? Let's think about this a little bit. If I chose the one on the right here, the t is greater than or equal to negative 7, well, if I put negative 7 in the natural log, negative 7, negative 2 is negative 9. We can't have log of a negative number. So we're actually going to go with the t is greater than 2. If I did the graph, it would become obvious why I'm doing that. Because we're looking for the intersection, remember? So this will be 2 to infinity, like that. And h of t. That's this last one. And we got negative t and then square root of t plus 7. Well, we already did t plus 7. That's up here. So this would be bracket negative 7 to infinity. Now our domain is the intersection. And if I look at the intersection graph-wise, intersection is where they're both shaded. So if I look at this one right here, this is negative 7 to infinity. There's negative 7, here's 2. Okay, so negative 7, and I'm going to positive infinity. Now this one is 2 to infinity. So here's my 2, and I'm going to infinity. Now remember what I said. We're looking for the intersection. The intersection of these two is where they're both shaded, which is from 2 to infinity. So our answer will be 2 to infinity. That's our domain. Sometimes if you graph it, it becomes really obvious. Up here, I just did kind of a think it through type of deal on the g of t. But if I had graphed it, I would have saw this. So let me save that. Next problems are evaluating a vector valued function. So this one's doesn't have our k component, so it's in 2 dimensions. Excuse me. T squared I plus 4t j, and a, we want to find where t is equal to 1. I forgot to put the r of t here. There you go. So we're going to plug 1 in for the t. So we got 1 squared, and then times, or I, plus 4 times 1j. So this one, the 1 squared is 1, so that gives us I. And 4 times 1 is 4, of course. So that's 4j. And that'd be our answer. Next one is s plus 3. So we're going to plug in the s plus 3 everywhere we have a t. So we have s plus 3 squared. And this one will be 4 times s plus 3j. And C, we want to find r of 1 plus delta t minus r of 1. Now let's find this in pieces. 1 plus delta t. So we're going to take our original vector valued function up here, and we're going to plug in 1 plus delta t for the t. So we've got 1 plus delta t squared I plus 4 times 1 plus delta t j. And if I multiply this out, take 1 plus delta t times 1 plus delta t, I'm going to get 1 plus 2 delta t plus delta t squared I plus 4 delta t j. Now let's find our next one here. So we're going to plug 1 in for t. So we're going to have 1 squared I plus 4 times 1j. Actually, we found that right up here, didn't we? So it gives us I plus 4j. Okay, so now if I subtract those, so we're going to take all of this. So we got 1 plus 2 delta t, 1 plus 2 delta t plus delta t squared. I was just listening, I heard phone ring. 4 plus 4 delta t j minus, and then I'll put it inside of parentheses because the minus has to affect both of these, I plus 4j. Well, the 1 inside the parentheses here that goes with our I is going to disappear with this minus 1. So we're going to be left with 2 delta t plus delta t squared I. The 4 that's here, this would be 4 times j, and I didn't put the vector notation on that, j. So 4j, and then this is a minus 4j, so that disappears. So we're going to have plus 4 delta t j. And that'd be your answer. This one's in 3 dimensions. So let's look at it. R of t is equal to 3t squared I plus natural log of tj minus 4k. Of course, I, j, and k are vectors, and we want to find where t is equal to 4. Yeah, 4. So we'll put 4 in for t. So we've got 3 times 4 squared I plus natural log of 4j minus 4k. 4 squared is 16 times 3 is 48. I plus natural log of 4j minus 4k. And that's our answer. Now, next one is where we want t to be -2. I didn't bold those, but those r's there should be bold. Well, if we plug in -2 for the t, so we're going to have 3 times -2 squared, I, plus natural log of -2, j, minus 4k. We can't have log of negative number, so this one is not defined. Save that. Time for my tablet to blow up. There we go. Okay, let's find this. Number 5. You'll find that much of the same vector formulas and so forth we used in previous sections apply in vector valued functions. Okay. Now here, what we're going to do is we're going to take the square root, and then we're going to take our component functions and square each one and add them together. So we got 3 square root of t squared plus t squared plus -e to the t squared. Well, 3 squared is 9, and you square the square root, and it gives just the square root and the second power cancel each other out. So this gives us 9t plus t squared. And when you square a negative, it becomes positive. And when you're raising one exponent to another exponent, you multiply the exponents together. So this becomes e to the 2t. And that's our answer. So nothing real surprising there. That's what we saw over and over with vectors. Now to review a little bit. And then we're going to apply this to our vector valued functions. Remember, if you got an initial point, P, with x sub 1, y sub 1, z sub 1, and terminal point is Q, x sub 2, y sub 2, and z sub 2. Define our direction vector. V would equal to, we take our terminal pieces, the x2, y2, and z2, and we subtract the initial, x1, y1, and z1. And that gives us a vector, and we label this as A, B, C. Then to find our vector valued function, we take our x1, this is off of our initial point, plus A, which is off of the direction vector, t, I, and then plus y1 plus bt, j, plus z1, c, plus ct, k, and so forth. And then our parametric equations is just these formulas here. X equals x1 plus at, y is equal to y sub 1 plus bt, and z is equal to z sub 1 plus ct. Let's look at an example of that. And there's different answers you can come up with on this. So if you look in the back of the book, they'll say answers may vary or something on these particular ones. Let's see. 2, 1, -3, and that's our initial. And our terminal side will be 4, 7, and -5. They say represent the line segment from P to Q by a vector valued function and by a set of parametric equations. Okay. First thing, let's label these. This is x1, y1, and z1, and this would be x2, y2, and z2. Nothing exciting on this, it's just a formula based. So we'll first find our direction vector, v. And we're going to take our terminal and subtract our initial. So we're going to have 4 minus 2, that's our x2 minus x1. And then our y2 minus y1, so we got 7 minus 1. And then we got negative 5 minus negative 3. 4 minus 2 gives you 2, 7 minus 1 is 6. And the negative becomes positive, so we got negative 5 plus 3 gives us negative 2. And this would be our A, this would be our B, and this would be our C. Now our vector valued function is given by this formula. So we've got R of t is equal to x1 plus AT I. And then we're going to have y1 plus bt and so forth. There it is. So plus y1 plus bt j plus z1 plus ct k. So x1 was 2 plus a, which was 2. So we got 2 plus 2t I. And y1 was 1 plus bt, so plus 6t j, plus z1 was negative 3 plus c minus 2t k. That's the first part. That's your vector valued vector valued function. Now the next part's pretty easy. X is just equal to what's before our I, so we've got 2 plus 2t. Y is just what's before j, which is 1 plus 6t. And z is equal to negative 3 minus 2t. Now, this is how they actually have us leave it. So they don't try to get those combined together in any sense. Remember, sometimes you'd solve for t and then you'd equate all these, but this is where they're stopping here. Well, let's take a look at this. This is just a little bit of review again. So we got this vector valued function, R of t, 5t I plus t over 4j minus 5k. And then we got 9t to the third I plus tj minus 7tk minus 7tk. And we're finding whatever this is. Remember the dot product when we're dealing with vectors? This is not multiplication. What we do with the dot product is we multiply what's before the i's together. So I'm taking 5t times 9t to the third plus, and then I'll multiply what's in front of the j's. So I got t over 4 times t plus, now I'll multiply what's in front of the k's. So I got negative 5 times negative 7t. So that gives us 45 t to the fourth plus 1/4 t squared plus 35t. And that would be our answer. Let me save that page. And then we'll look at the next problem. I think the next one is a graphing one. Yeah, it is. So we got match equation with this graph. And I should have labeled these in some way, like this is A and this is B. But we'll take a look at these. Cosine 3t I plus sine of 3tj plus tk, and t is between 0 and pi. And my wife's coming in here bugging me. There we go. And our other one, natural log of t I plus 2tj, plus tk, and 0 to 3. Now, of course, you can have the t represent time. If this was simulating or even modeling something in real life. So here it hasn't started, and then it comes around here and starts twirling around. Well, we kind of know just by looking at this which one's which. Cosine plus sine, that first example we looked at, that forms a circle. So if I rotated this, looking at the x and y axis, we'd see that it has a circular pattern. And then the t just causes it to go up and down like that. The natural log. Well, look how this curve here is shaped. That looks like a natural log. But let's pretend I don't see that. Let's graph these on our utility. And let's see. I'm going to do equation, do a curve. And I'm going to type in cosine 3t. And here I'll put in sine 3t. I know this is kind of small and you can't see it. But the x equals is cosine 3t, the y equals is sine 3t, and the z is equal to t. This one says t low, and I'll put in 0. And the t high is pi, so I'll put in pi. And then I'll click OK. Now if I do view axis, you can see which one it matches. Matches one on the left. So our cosine one here is the one on the left. Now other one, let's plug that in to our utility. And window disappeared. Shouldn't have closed it. View box. Okay, well I'll just close this and start over. No. So I do window, 3 dimension, do equation, curve, and here I'm going to have natural log of t. So I'm on the x equals, so I do natural log of t. T's inside of parentheses. And then I got 2t and t. So I put in 2t and then t. And this is going to go from 0 to 3. So t low is 0 and t high is 3. Now click OK. And do a view axis. And I have to rotate a little bit to actually see it. You see how if I rotate it such that I only look at a couple of the axes, not that I can get it where I want, and we can see the shape of the natural log appear, depending upon how we rotate it and so forth. So that one matches the one on the right. Now I have to admit, if I did these by hand instead of cheating and using our WinPlot utility, it would take me a little bit, and they wouldn't look good anyway. So we'll keep using our wind plot. Okay, this one says sketch a curve represented by a vector value function and give the orientation. So r of t is equal to t squared I plus t plus 3j. Now, remember our component functions. This is x, so we got x is equal to t squared, and we got y is equal to t plus 3. Now, I can solve this over here for t, so I take 3 over. We get y minus 3 is equal to t. And we can take that and we can plug it into the other one. So we can plug that into x is equal to t squared. Well, we just said t was y minus 3. So we got x is equal to y minus 3 squared. Now, if I look at just that in terms of my x's and y's, we lose the t component, which doesn't tell us the orientation. But let's take a look at what this graph looks like. If I were to plug in y is equal to 3, 3 minus 3 is 0, 0 squared is 0, so we get x equals 0. So this would be a point. If I plugged in y is equal to 2, 2 minus 3 is negative 1, negative 1 squared is a positive 1, so that would be this right here. If I plugged in 4, 4 minus 3 is 1, 1 squared is 1, so we would also get this right here. So this is what our graph would look like. That's assuming there's no restrictions on the t value, and that's in terms of x's and y's. But let's graph this in our utility and see what we get. I'm gonna close that. Go to Window, 2 dimensions, do equation, and hopefully I remember where it's at. There it is. It's the second one. Then it asks us for f of t and g of t. F of t is t squared, so I'll do a t caret 2. And the other one is t plus 3. So t plus 3. Now for the t value here I got 0, and maybe I put the high as 4. Now, this may not give us the entire picture, so you have to be careful with the t values when using this. If I click OK now, you see it didn't give us the entire piece, did it? If I go back to Edit, instead of 0, let me put in negative 4. Then you see we get more of the picture. And let's see. I'm using my up and down arrow to move that around. I use my page up and page down to zoom in and zoom out. So that gives it to us. Well, you looked at, well, I still don't see the orientation. If you click Edit here, this box asks you where to put the arrow at. So I click this, the little check box next to the put arrow at t equals, and I could put that at, I don't know, t is equal 1, and click OK. And that shows you the orientation. So I could come over here and try not to screw that up. And you have this. So that shows you how it goes. Now, since it doesn't give us any starting value for t, you can put the arrow anywhere. Okay, let's look at number 10. R of theta is equal to 2 cosine theta I plus 5 sine theta j. Now again, looking at 2 cosine theta, that's our x, so we got x is equal to 2 cosine theta, and y would equal to 5 sine theta. If I solve this for cosine, divide both sides by 2, I'd have x over 2 is equal to cosine theta. And over here, divide both sides by 5, I get y over 5 is equal to sine theta. Now I can square both sides, so this gives us x squared over 4 is equal to cosine squared, and this would give us y squared over 25 is equal to sine squared. Well, now we can add those equations together like we did in the previous problem, or somewhere in the previous problem. We'll add the x squared over 4 plus y squared over 25. So I got x squared over 4 plus y squared over 25. And we'll add the cosine squared plus sine squared. So we got cosine squared theta plus sine squared theta, which is equal to 1. So this becomes x squared over 4 plus y squared over 25 is equal to 1. Well, that's an ellipse. If I come here, my x, that'd be right here, and for my y, that'd be right here. I'm not going to spend a whole lot of time making this look good. That'd be more or less our graph. The orientation. We could plug in points up here and help us see what that is, because this is based upon the angle. Or we could use our utility, which we'll do. We use WinPlot. I'm just going to go ahead and close that, so I start over fresh. I'm going to choose Window, 2 dimensions. Choose Equation, and then our parametric. And our first one is 2 cosine theta. So I got 2 cosine, I'll put t. And this next one is, what was it, 5? Yeah. 5 sine t. And I'll put 0 here, and then I'll put 2 times. I'm not sure if I needed the asterisk, but I'll put an asterisk for multiplication, then pi for pi. And I'll put the arrow at, I don't know, pi over 4. So I did pi divided by 4. I'm not sure if you can see that, since it's kind of a small window. Unfortunately, it won't let me resize it. And then I'll click OK. And you see the arrow there to indicate the orientation. Now, unfortunately, with this utility, is if you don't pick the right values for t, then you're not quite sure if you got the entire picture. Like if I had, instead of putting in 2 pi, if I put in pi, I would come up with this. And I think, okay, that's my answer. So it's kind of handy to switch these to our rectangular values and see what the true picture should look like. Then we can double check it with the utility. Okay, let's look at this one. This one's getting into the 3 dimensions. Let me save this. There we go. And we got r of t is equal to t plus 2 I plus t minus 1 j plus 2t k. Well, very easy to graph with our WinPlot. I'll come over here, close that, go into Window, 3 dimensions, choose Equation, and choose Curve. And here I'm going to have t plus 2. And next one is t minus 1. And then z equals is 2t. 0 to 2 pi is what it defaults to. Leave it at that. No, I don't think I want to leave it at that. Let me put a 4 there. That'll make it a little bit better, I think. And let me click OK. Now if I choose View, Axis, Axis, I get this picture right here. And for our answer, we just sketch that down. Now, it's not hard to do this. I mean, it makes sense that it's a line. Because when you think about it, if I ignored like the z component here and looked at only the x and y, well, x is equal to t plus 2, y is equal to t minus 1. That would be a line. And if I ignored any of these pieces, everything's linear. Now, if I was doing this by hand, this one I may attempt. I'm not very good at doing these by hand. If I looked at, for example, t is equal to 0. If I put t is equal to 0 in here, that's why we looked at evaluating functions. So if you're doing this by hand, you'd basically be building a t-chart of sorts. So you got 0 plus 2, so that gives us 2i. 0 minus 1, so we got minus j. And then we got to put a 0 here. 2 times 0 is 0, so that's 0k. So it'd have 2, negative 1, and 0. So we go 2, and negative 1, which would be right here, and 0. So it'd actually be sitting right there. We wouldn't be having erased any. So that'd be our first point. Now if I plugged in another one, t is equal to 1. Put 1 in here, then I would have 3. 1 minus 1 is 0. 2 times 1 is 2. So we'd have 3 out to here, then 0, so y would be 0, and then z would be 2. So go here, and it's kind of hard to see. I go up this distance here, and then we'd have this second point. And again, I don't do 3D very well. T is equal to 2. If I put 2 in there, 2 plus 2 is 4. 2 minus 1 is 1. 2 times 2 is 4. So I go out to 4, and then 1, and then up 4. So we'll go 4, 1, so we're sitting right here. And then I go up at this distance here. And I don't know, that's as good as I'm going to get in 3D. So we'd have a line going up like that. It's much better to plug in utility here because it's a lot easier to see. And again, just sketch this as best as you can. So you don't have to put a huge amount of effort on it. You can see how we can export this. So we can get a much better picture by exporting this and importing it into a document than we can by trying to hand draw it. Okay, let's look at this one. And we've already kind of seen this type. Not exactly this one. Because we're going to see, so you got ti plus 2 sine tj plus 3 cosine tk. Now notice there's different numbers in front of the sine and cosine. It's no longer going to be a circular pattern. So let's plug this in and see it. And not only that, but the sine and cosine are no longer on the I and j like that previous example was we looked at, but they're on the j and k. So we're going to see what that does to our pattern. Before, our loopity-loop graph went along the z-axis. Let's see what this does. Close that. And then do window, 3 dimensions. Do equation, choose curve. T, 2 sine t, so x is equal to t, and then y is equal to 2 sine t, and z is equal to 3 cosine t, like that. And yeah, that's probably good enough, 0 to 2 pi there. We'll put the arrow for the orientation. I don't think it's asking for that, but we'll put that at pi over 4. And now press OK. I'll do a view axis. Now if I rotate it, see how the curly part is going along, instead of along the z, it's going along our x-axis. And if I rotated this such that I only look at the I'll get there eventually. Maybe. Yeah, I'm not going to be able to get it perfect. But if I look at it with along the y and the z axis, I see it's an ellipse. It's no longer a circle. The ellipse comes from the fact that we have different numbers in front of these. If I went here, did an edit, and instead of putting a 2 and a 3, put a 2 and a 2. And click OK. See how it becomes a circle? Put a 3 back there, like that. And again, just sketch this down as best you can. And if you don't even want to sketch it down, if you just want to export this into Word or something like that, all you do is you do a File and Bitmap to Clipboard. And then you go into Word and you just paste, and then you have it. So, and I don't have any problem with that. Now, this one says sketch a space curve represented by the intersection of the surfaces, then represent the curve by a vector valued function using the given parameter. I'm not going to actually do that part. This x squared plus y squared plus z squared is equal to 10. This is a sphere, and the x plus z is equal to 4 is a plane. And you can imagine when a plane intersects a sphere, what will happen. But let's go ahead and do the second part. If I tried to sketch that, it would take me quite a while. And if you want to do that on homework, that's fine. But that's unfortunately this wind plot, I can't figure out how to actually graph these, which would be where I'd want it to be. But let's go ahead and put it into a vector valued function. So we're going to start with this parameter. And I got room. Let me save that. Start a new page. And we got x squared plus y squared plus z squared is equal to 10. And we got x plus z is equal to 4. And they tell us that x is equal to 2 plus sine t. Okay. Well, I want to take this x is equal to 2 plus sine t and plug it into the x plus z is equal to 4. So we replace the x with 2 plus sine t. So we're going to have 2 plus sine t plus z is equal to 4. Now I'm going to solve for z, so I take those over. Take the 2 plus sine t to the right side. So we get 4 minus 2 minus sine t. 4 minus 2 is 2, so we got 2 minus sine t. Okay, so we got x and we got z. So let's find out what y is. So I'm going to come over here to my x squared plus y squared plus z squared is equal to 10. And we just said x was 2 plus sine t. So plug that in. Y squared, we don't know. Z squared. Well, z was 2 minus sine t squared equals 10. And I'll come down here and when I FOIL this, 2 plus sine t times 2 plus sine t, that gives me 4 plus 4 sine t plus sine squared t. And plus y squared. When I FOIL that, I get 4 and minus 4 sine t plus sine squared equals 10. Now here's a 4 sine t, here's a negative 4 sine t, so those are going to cancel. And we got 4 plus 4, that gives me 8. Sine squared plus sine squared is 2 sine squared. And somewhere we have y squared, there it is, equals 10. Take these over to the right side. So we've got y squared is equal to 10 minus 8 minus 2 sine squared. 10 minus 8 is 2, so we've got 2 minus 2 sine squared. I want to factor out a 2. And that leaves us 1 minus sine squared, which is equal to cosine squared. 1 minus sine squared is cosine squared. Now we'll drop our squared off, and then we'll put a square root around the other side. So we get y is equal to the square root of 2. And then this gives us cosine t. So now we know what our x, y, and z is. So let me jot that down. X is 2 plus sine t. And y is equal to the square root of 2 cosine t. And z is equal to 2 minus sine t. So then our vector valued function, we're going to have 2 plus sine t I plus square root of 2 cosine t j plus 2 minus sine t k. That's our vector valued function. Okay, well, let's graph this. So come over here, I'm going to close that. And do a window, 3 dimensions. Do equation, choose curve. What did we say x was? 2 plus sine t. So 2 plus sine t. Y is equal to the square root of 2. So sqrt. Beginning parentheses 2, closing parentheses. Square root of 2 times cosine t. I don't know if I needed times there, but I'll do an asterisk. Cosine t. And then 2 minus sine t. And 0 to pi is probably okay. And I'll click OK. I'll do a view axis. Like that. And that's what we came up with. Now imagine, back here, I said I was too lazy to actually do it, but imagine if I had gone through the effort, use your imagination here, and I said that was a sphere. So we got this right here. And if I had a plane intersecting this, so think of cutting this, then what we end up with. This is not going to look good, but it'd be it'd be that right there. So it makes sense when you come up with your graph that it would look like this. Like I say, ignore this graph. It's much easier to imagine a sphere, and then you're cutting a sphere with a plane. Let's see, was that all they wanted on that problem? Okay, yeah. Okay, let's talk about limits. Let me save this. Actually, I got room for one more. So we got limit as t goes to pi of secant t I plus tangent t j minus t squared k. Very simplest way to evaluate a limit, remember, is to plug in the value. So we'll put pi in for t. So we're going to get secant pi I plus tangent pi j minus pi squared k. Now, remember what pi is. Pi is over to here. So we're sitting here at this point. Our secant is 1 over x, and our x value here would be, this is -1, 0. So we have 1 over -1, which gives us -1, so this gives us negative I. And I got up pretty early this morning, so let me think that through. Secant is 1 over x, and pi is over to here. X is -1. Yeah, that's right. Okay, tangent. Tangent is y over k. Y over k. Y over x. I better go to bed. Well, here's y, and here's x. So 0 over -1 is 0. So that drops away. Minus, and then pi squared k. Let me save that. And let's look at the next one. Good thing we're about done dying of thirst here. Okay, so 15. Limit as t goes to 0. Excuse me. Tangent t over t minus e to the tj minus 3t k. If I plug in the 0 here, we're going to have tangent of 0. Now tangent is 0, tangent is y over x, so we're going to have 0 over 1, which is 0. And if I put 0 down here, we have 0. So that doesn't work there. Here it works fine on these two. So I can just go ahead and plug in the 0 on these. But on this first one here, we have to use L'Hopital's rule. Now remember, with limits, we can split them up. So I could write this one separate than the rest. And plus limit as t goes to 0 of negative e to the tj minus 3t k. Okay, now I'm going to use L'Hopital's rule on here. Remember that. Means if you end up with 0 over 0 and infinity over infinity, I can't remember all the different forms, but then you can take derivative of the top, derivative of the bottom. So let's do that. Well, the derivative of tangent is secant squared. Derivative of t is 1. I. Now over here, if we go ahead and put 0 in, so we're going to have a minus e to the 0 j minus 3 times 0 k. Okay. Well, now if I put in 0, secant by itself is 1 over x, and if I put this in for 0 there, well, let me draw it. If I put 0 in, our angle here would be this right here, and our point would be 1, 0. And secant is 1 over x, so 1 over 1 would be 1. 1 squared is 1, so this would be I. Anything to the 0 power is 1, so this would be minus j, and that drops away. So that would be your answer. Now the last thing talks about the where it's continuous at. And this is, again, pretty similar to what we've seen already. You look to where each component function is discontinuous. And where the component function is discontinuous is where the vector valued function is discontinuous. Well, if I look at t squared, so f of t is equal to t squared, this is continuous everywhere. There's no place where that's discontinuous. No place where it's undefined. If I look at my 2 over t minus 3, my g of t, well, if I set the denominator equal to 0, so I got t minus 3 equal to 0, I'd get t is equal to 3. So this is discontinuous at t is equal to 3. Which means my vector valued function, if I look at where it's continuous, it's continuous from negative infinity, and this is assuming that negative values make sense for this particular problem for t, up to 3, and then parentheses under 3 means we don't include it, union 3 to positive infinity. And that'd be your answer. And that's the end of that lesson, so let me save that page. Which is good, I'm tired. Bedtime. Becoming an old man. He's ready to go to bed at 7. Okay, so CF.